things I needed to say. So now I can start off by welcoming Jim Wilde, who we have here to speak today. So Jim Wilde is a professor of space physics at the Lancaster University Department of Physics. His research focuses on investigating solar terrestrial connections, the impacts of space weather, and also the interaction of Mars's plasma environment with interplanetary space. Jim is also heavily engaged in science communication. He held an SDFC Science in Society Fellowship and was also awarded the RAS James Dungey Lectureship in 2018. So today, Jim will be speaking on space weather, living with our star. So I'll hand it over to you, Jim, so you can start sharing your slides.
Thanks, Jasmine, and thanks very much to the MIST UK community for the invitation to come and speak on this new online seminar series. I think it's a really good idea that out of the current situation we've kick-started this community series of seminars. What I've tried to do today is put something together which might have just a little bit of something for everyone. These seminars, I understand, are recorded for posterity and are going on YouTube. So it might be a way in which people who are less familiar with what goes on in MIST, in the MIST community, the magnetosphere, ionosphere, and solar terrestrial community, what we do to find out a little bit more. So I've tried to make it a little bit of a sort of buffet with a bit of something for everyone. And what I'm going to do is I'm going to share my screen now, and so let's give it a go. Okay, and if the magic of the internet works, there we go. And we get our first comedy subtitling error there in the first slide, but there we go. So, what I'm going to talk about today is a presentation, Space Weather, Living with Our Star. And some of this actually was based on the James Dungey lecture I gave at the RAS not so long ago, which was a presentation intended for people who weren't necessarily specialists in the space physics community. And I've retained some aspects of that, as I've said, to try and get a little bit of interest in there for everybody. So to begin with, what is space weather? I'm pretty sure most folks on the call, most of the scientists on the call will be aware of what space weather is, but it never hurts to recap. So we're really talking about the effects on the space environment around our planet and how those are impacted by the electromagnetic fields and material which are emerging from the sun and traveling out through the solar system. And so what I'm going to do in this seminar is just give a little bit of a history and background to that, and then try and drop in a few policy and sort of society issues, because as scientists we tend to be very focused on our little niche area of research, but these obviously have very big impacts potentially on society. So I'm going to try and drop in some of those issues as well. And then towards the end, I'm just going to flag a little bit of recent research that's going on at Lancaster in the field of space weather research. And so, first of all, the sun isn't new, the earth isn't new, space weather isn't new. And one of the very obvious signs that space weather has been impacting our planet for a long time is the aurora borealis, the northern lights, and the aurora australis, the southern lights. And there's no talk on space weather you can give without some gratuitous movies of the northern lights. So here are some fantastic time-lapse videos of the northern lights recorded over Scandinavia. Now, the northern lights are simply a consequence of material traveling from the sun out through the solar system, mainly subatomic electrically charged particles that are interacting with the region of space around our planet and our planet's own magnetic field, and the changes in that magnetic field and the electric fields around our planet work like a natural particle accelerator and accelerate material, subatomic charged particles in towards the upper atmosphere, causing it to glow, much like inside a neon lamp. And so this natural light show has been going on for tens, hundreds, thousands of years, millions of years, ever since our planet's had an atmosphere and a magnetic field. And so humans have been looking up at the night sky and seeing the aurora borealis since the earliest people walked the planet. And this is the natural impact of space weather. Nothing new there at all. However, in the last couple of hundred years, we've had a better scientific appreciation of what we're looking at here. And so I'm going to sort of short circuit and jump straight over a lot of the science and take us back to about the beginning of the 20th century, when Christian Birkeland, who's pictured here in his laboratory, had undertaken several expeditions up to the high Arctic parts of Scandinavia, and had observed, when doing magnetic mapping, that when the northern lights were overhead, the magnetic sensing equipment used for surveying and other things tended to go completely haywire. And he became convinced that the northern lights were an electromagnetic effect that were disturbing basically compass needles on the ground. And so he went back to his laboratory at the University of Oslo and created several experiments to try and recreate the northern lights in the laboratory. And here you can see one of his very famous Torella experiments. This thing that looks like a goldfish bowl, and I'll try and highlight it. Okay, this thing looks like, sorry, a big fish tank in the center of the picture, is a partially evacuated glass chamber. So most of the gas inside has been removed. And then at the center of it, you can see this ball. This is a model of the Earth with a magnetic field inside. So it basically has a bar magnet inside. And by passing electric current through the gas, what Birkeland was able to do was to be able to create the lights of looks like a mini aurora, the northern lights around the northern and southern magnetic poles of this planet inside his experiment. And from this, he became convinced that the northern lights must be due to electrically charged particles interacting with the upper atmosphere, and that these particles had to have come from space, probably of a solar origin. And really, that was hitting the nail on the head just over 100 years ago. Now, Christian Birkeland did a lot of this pioneering work. He was actually a bit of a character. I always like to drop into these talks, that you can see him in his laboratory wearing his fez here. So Birkeland was a bit of a character. He would alternately joke saying it would keep his head warm, but he also would sometimes say it was to protect him from the harmful X-rays his machines produced. And apparently the University Inspection Committee, who was supposed to inspect all laboratories in the university every year, basically stopped going into his laboratories because of the sort of risk of being electrocuted, the funny smells, the flashes, the bangs, and these kind of things. So perhaps it was a clever disinformation scheme to keep the university administrators out of his laboratory. But moving on a little bit from the beginning of the 20th century, when we had Christian Birkeland doing his experiments in Oslo, if you fast forward now 20 or 30 years, sort of by the 1930s, the idea had emerged that the sun would occasionally emit a cloud of material into the space environment. So you could see active features on the surface of the sun. And so the idea was that every now and again, the sun would basically belch out a load of solar atmosphere into space, and this could breeze past the planet. And so here we have a figure from a paper in the 1930s. And in these figures, these are from papers by Chapman and Ferraro in the early 1930s. And what you're seeing is the concept is we have the Earth in the center of the figure, and the sun is off to the left-hand side. And as a front of this material, sort of a wave of material passes by the Earth, it goes around the planet a bit like a river flowing around a rock. Now, that's, again, not too far from the truth. At the time, it wasn't understood that this material coming from the sun was actually electrically charged. So it was a plasma. It was a gas in which some of the subatomic particles had been broken down. Sorry, the atoms inside had been broken down into their subatomic constituents, which are electrically conductive. And it wasn't understood that electrically conductive cloud, as it moved out from the sun, dragged with it some of the solar magnetic field. So it wasn't really understood that this was a magnetized plasma that the Earth was being engulfed in. And it was also thought to be a sporadic thing. So most of the time that space was a vacuum, but every now and again we would be washed over by some material from the sun. Now, by the beginning of the space race, that attitude was starting to change a little bit. And so here we have a famous picture of three folks holding up a model of the Explorer 1 spacecraft, which was launched in February 1950. And in the center of this trio is James Van Allen, by now, who is now one of sort of the pioneers of the space age measurements of the geospace environment around our planet. And to his left, on the right hand side of this picture, is Werner von Braun, sort of the father of the rocket engine, if you like, that took the Apollo astronauts ultimately to the moon. And again, it wasn't really understood what was going to be in space. And when Explorer 1 was launched on its nose cone, there was a cosmic ray detector, effectively a Geiger counter, which it was thought might detect particles of subatomic electrically charged particles coming from outside our solar system. But there is a very famous quote from one of Van Allen's colleagues that when they turned on the instrument, it was engulfed in subatomic particles, and one of his colleagues, Ernie Ray, was noted to say, "My God, space is radioactive." And so there were lots of alpha particles and beta particles. So these are helium nuclei and electrons flooding into their detector. And so space isn't empty; it's full of these subatomic electrically charged particles. And the discoveries that were made later led to the naming of the radiation belts around the planet as the Van Allen belts. And so these are regions of trapped subatomic particles. So electrically charged subatomic particles that become trapped within the Earth's magnetic field and form these belts. And here is a schematic from the time and a picture of Van Allen on the cover of Time magazine. And so these radiation belts surround our planet and are today one of the areas that show the link between our planet and our nearest star, which are particularly relevant to the topic of space weather. And so what is this space weather term I keep mentioning? Well, really, it's how the environment around our planet can be affected by the radiation, the electromagnetic fields, and the material from our nearest star, from the sun. And so I've stolen a schematic here from the European Space Agency, but it just sums up some of the range of our systems, our human systems that are impacted by space weather. Now, I'm not going to in 30 minutes here today, I'm not going to have time to talk about all these. So I'm just going to dabble on and touch on a couple that I'm interested in. But these aren't just things in space. So you might think space weather, changing in the space radiation environment, would have an impact on satellites or on astronauts. And of course they do. And that's a very big part of what space weather is all about. But also these effects can cause, they can cause that you can spot the effects of space weather at ground level, which is what I'm going to start talking about in the next part of this talk, really. And so really, I'm going to focus here on some of the things that generate things like geomagnetically induced currents in power systems, and also how that then goes on to impact other kinds of everyday life here on the surface of the Earth. So space weather is nothing new, as I've said already. It's been around since the creation of the planet. However, more recently, human technology has got to the stage where we are building societies that are reliant upon technologies that are sensitive to space weather in ways that pre-technological humans weren't so. And so it's important that we understand these risks. So to kind of finish off our background history tour, it's worth us just spending a couple of minutes reminding ourselves where some of the where some of these natural effects are coming from. So in this animation, what I've done is I've just taken a movie of, I can't see if my movie's playing or not. There we go. Okay, so my movie doesn't want to play. Perhaps it's playing on Zoom, I'm not sure. What we have is that the sun is surrounded by the solar corona that we can see here, so the outer atmosphere of the sun, and this is a coronagraph. This is an image of the solar atmosphere taken from a spacecraft with a camera on, which obscures the sun in this black zone in the center. And actually, I've just plopped in an image of the visible solar surface there, so you can see where the sun is and roughly how big it should be. But the solar wind is this outpouring of material, of basically about 1,000 tons per second of material from the sun. It constantly streaming out 24 hours a day, 7 days a week. And that material streams out through the solar system, carrying with it the sun's magnetic field. Well, when that material arrives at the Earth, it encounters the Earth's magnetic field, and a strong interaction can occur. And this was actually first proposed by Jim Dungey of Imperial College London, back in the middle of the last century, so in the 1960s. And so here we have a freehand sketch of the time showing an interaction between the magnetic field coming from the sun and the Earth's magnetic field through a process called magnetic reconnection or magnetic merging. And effectively what happens in the sun's magnetic field, which travels out through the solar system into the interplanetary magnetic field, hooks in to the Earth's magnetic field and peels it open. So our magnetic force field, which shields us from the solar wind, is actually susceptible to being opened up by coupling with the magnetic field inside the solar wind. And that coupling is very time variable. So sometimes it's a very efficient coupling and other times it's less efficient. And so I don't know if my next movie is going to work or not. Oh, it is. There we go. So that's good. So we can see here actually that coupling, rather like James Dungey's cartoon from the 1960s, you can see on the left-hand side of this upper animation is a magnetic field inside the solar wind coming on, and it arrives at the front of the Earth's magnetic field, and it couples in with the Earth's magnetic field, and the field line at the Earth, on the Earth's day side pointing towards the sun, gets opened up on the day side and peeled back over the polar regions, and that same connection process, actually the same reconnection process, then closes off field lines on the tail of the Earth's magnetic tail on the night side of the Earth. And we get a cycling system set up known as the Dungey Cycle. And so the Earth's magnetosphere, the region of the Earth's space environment, which is dominated by the Earth's magnetic field, is set in motion by this coupling with the interplanetary environment, this magnetic coupling. And what I want to derive from this is on the other animation I have here, if it works, is that we actually get a stirring up of the Earth's upper atmosphere as a consequence. So on this right-hand panel, we've got a view looking down on the polar region, and as those field lines are basically being peeled back over the polar region from the daytime, where it says 12 LT, so that's 12 local time or noon, as the field lines get peeled over towards midnight, a electromagnetic connection sets up a stirring of the upper atmosphere in a convection cycle. And so we have electrically charged gases in the upper atmosphere, in the ionosphere, set in motion by this coupling with the space environment. And in the cartoon to the bottom left is a simplification, if you like, of some of these electrical current systems that are set up as a consequence, because we're stirring up electrically charged material. And we're moving that electrically charged material through magnetic fields. We get current set up in a variety of directions. So we are sitting on the ground beneath this upper atmosphere, this ionospheric region that is set in motion by a coupling with the solar wind and the interplanetary magnetic field. So the sky above our heads is being altered and changed due to connections with our nearest star. And so this is why space weather starts to have an impact. Now, there's another quite well-known cartoon in the space physics community that attempts to simplify this, but actually I like this cartoon because it really shows us, just even in its simplified way, just how complicated this system is. The Earth's environment doesn't stop at the top of the atmosphere. We are coupled into the space environment, and we need to understand that space environment more clearly if we're to understand the impact it has here along the ground. And so I'm not going to try and unpick this entire cartoon, but a lot of what we're going to talk about here in the latter part of this talk is summarized by some of the physical processes that go on in here, and that the folks on this, listening to this seminar in the magnetosphere, ionosphere and solar terrestrial community, are some of the world leading experts in a variety of these different processes. So how's this going to affect us? So I just got one bit of data here and a simple crude schematic I knocked up. But basically, what we have here are some measurements of that natural environment. So actually, the bottom three panels here, we have some data here from a paper in 2006, but actually taking data from the early 1990s. And what we have on this bottom panel here is measured against time for just under 24 hours, is the strength of the north-south component of the magnetic field of the Earth measured at the ground. So this is in effect a time series of the intensity of the northward component of the field. And this is not only there is the magnetic field of the Earth, but then superimposed upon that are magnetic fields created by some of those electrical currents in the upper atmosphere. And so this is kind of shown on the schematic on the left-hand side. If you imagine we have an electrical current flowing the upper atmosphere by space weather, connecting it into the space environment, then that's the red line there. Imagine like a wire flowing through the upper atmosphere. Then around that, we have set up magnetic fields. And so this is rather like the kind of high school science where you use your right hand to show if you have a current in a wire, you can work out which way around the magnetic field will go around that current in the wire. Well, same thing's going on. You'll have a horizontal current in the upper atmosphere around which flow magnetic fields, or sorry, our magnetic fields are set up. And so if you're sat on the ground beneath them, you will be able to sense those magnetic fields. Now, these currents in the atmosphere are very rarely stable. They're generally fluctuating up and down as their intensity increases and decreases. So the magnetic fields sensed at the ground fluctuate up and down over time as well. And so that's exactly what's being shown in this right-hand bottom panel. We're seeing the magnetic field intensity in the north-south direction being adjusted, modified by an electrical current in the east-west direction above it. And that's over a course of almost a day. And what you can actually see here is in the center panel of these, you can see instead of the intensity of that field, you can look at how fast it's changing over the day. And what you can immediately see is that there is a very large fluctuation at the beginning of this time series as this is presented, corresponding to a spike in the data. And then there is some more towards the end as well, over here on the right-hand side. And so you can see from this, not only is this, you can see the strength of the field changing, but also how rapidly it's changing. And then if you plot above it, the electrical currents flowing from the ground to a transformer in the electricity supply grid. So in my cartoon on the left-hand side, I drew a transformer connected to a three-phase power grid. You can actually get electrical, geomagnetically induced currents set up in the surface of the Earth because you have a fluctuating magnetic field. The fluctuating currents in the atmosphere generate fluctuating magnetic fields around that current. So at ground level, you'll have a fluctuation in the magnetic field over the surface of the Earth. Now, fluctuating magnetic fields are very closely connected to electrical currents through Ampere's law. That's how we generate electricity. And actually, these fluctuating magnetic fields will generate electric fields, which try and push currents through the surface of the Earth. Now, the surface of the Earth, the Earth's crust is not a great conductor, but if you have a power grid placed on top of the surface of the Earth with transformers every so often that are electrically earthed and connected to it, then some of those electrical currents will try and flow up through the transformers and through the lines rather than through the surface of the Earth. And so what we have here on the right-hand side, again, as we go back to our data from a day of data and this is data from Normiarvi in Scandinavia, you can see that we have electrical currents, typically a few tens of amps, flowing through the power grid, which are quite closely related to when we're seeing rapid fluctuations in the Earth's magnetic field being driven by these ionospheric currents in the upper atmosphere. So this is evidence that electrical currents in our human-made systems are being driven by natural fluctuations in the environment around us. And these are going on all the time, but it becomes interesting when you start to think about when does it get severe. And so what I've done is I've jumped straight in and gone from that sort of simple discussion of electrical currents in the upper atmosphere driving currents in power grids. I've jumped over here now to a document called the National Risk Register for Civil Emergencies. And let me just see if I can come back to something. We have here the National Risk Register for Civil Emergencies, which is a document produced by the UK government, and which is intended to show how the government considers various risks to our society. And so this is the 2017 edition of this document, and you can Google this and find it online. And there is a grid in this document which shows the likelihood of an event occurring in the next 5 years, going from 1 to 5, 1 being not very likely and 5 being very likely. And then the impact severity if that event did occur, 1 being not very high impact and 5 being a very high impact. Now, in this, I mean, at the time of having this seminar, which is August 2020, obviously we're in the middle of a global pandemic, and you can see actually, you can see this little symbol here. This is the pandemic influenza risk, which is thought to be quite likelihood of occurring and would have a high impact when this document was written in 2017. But there are other things in here as well, which you might recognize. So we have, for example, this is extreme cold weather. Is thought to be very likely and would have a big impact on our society. But there are other things as well, emerging infectious diseases you can see in this one. And this little icon I'm pointing to here is this little solar system is in fact space weather. So space weather sits in the UK government's National Risk Register of Civil Emergencies as something which is quite likely to happen and could have potentially a high impact. So this is something which is already factored into our society's thinking. So I just thought I'd unpick that a little bit in the next couple of slides. This is actually quite an interesting document as well. I recommend it's worth going and having a look at. There is a whole section on space weather, and the idea is it lays out to the reader roughly what space weather is, why it could be a risk, and what people are doing about it. So it's worth document worth going to have a look at. What people tend to focus on is extreme space weather. And that's the kind of high impact, low frequency event, which is quite tricky to plan for. So space weather is going on all the time. You can go to the Arctic Circle on any dark night of the year, and there's a reasonable chance you'll see some of the northern lights going on. But the kind of space weather which could potentially have an impact on, say, satellite operations or the power grid is a bit less common. And so one of the reasonable questions you might ask is, how extreme can it get? How bad can it get? And so it makes sense to think about other natural disasters, how we plan for those. So you can imagine I've got some pictures here of volcanic eruptions, or you've got a tsunami there, or a devastating earthquake. These things are very hard to plan for. And it could be called into question, is there a necessity to plan for it? You might imagine if you live on the edge of the ocean in a relatively in not a wealthy country, you can imagine there might be tensions between, say, spending money on healthcare or transport or education or research into tsunamis or a tsunami warning system. And actually getting that societal balance right to put the money in the right place for a risk which is probably not going to happen in the next 10 or 20 or 30 years is very challenging to do. But ultimately, if those events happen, you can imagine people would rightly ask, why weren't we prepared for it? So these high impact, low frequency events can actually be very challenging to deal with. And one of the ways you deal with them is to work out, well, what is the risk and how bad could it be? And usually with the space weather risk, what people will do when they want to cite how bad it can be is they'll refer to the Carrington Event. Now, the Carrington Event was probably the largest space weather event on record, certainly in sort of modern scientific era. And was an event which was, at the time, well, we have here an extract from the Monthly Notices of the Royal Astronomical Society from 1860. And it's reporting a sighting in early September in 1859 by Richard Carrington, who was, I guess, a gentleman astronomer of the time, who was making observations of the sun with his helioscope from his home. And he was drawing these beautiful images of sunspots, groups on the surface of the sun. Now, sunspot groups are evidence of heightened magnetic activity in the solar atmosphere. The heightened activity actually suppresses the convection in the outer layers of the sun and gives slightly darker regions. But they're evidence of increased magnetic activity, and he was studying these and drawing them when he observed a flash, a solar flare. He observed in real time as it happened. And actually, the story is he ran off to go and get the housekeeper to show her what was happening. And by the time he came back, it had actually stopped. So there's a good bit of observational guide out there that if you ever see something interesting, keep watching. Don't run off to go and tell somebody else. But what that was the solar flare, the sort of the flash bulb, the release of radiation to do with this activity on the surface of the sun associated with a spot group. But what he couldn't know was at a similar time, a huge amount of solar material was erupting from the solar surface and heading out towards the Earth. And it transited the 150 million kilometers between the Earth and the sun very rapidly, probably about 24 hours. Normally these things in normal times would take sort of a couple of days, a few days. And it created a huge geomagnetic storm. And we know that because at the time we have, for example, from the British Geological Survey archive, we've got recorded at Kew Observatory magnetic field measurements from measuring the Earth's magnetic field and changes to it imposed by currents in the atmosphere. And we know that as the radiation from the solar flare arrived that Richard Carrington saw, it tickled the upper atmosphere and increased the electrical conductivity of the upper atmosphere, allowing slightly increased currents to flow, which were detected almost instantaneously. As the flare radiation arrived, there was some increases in electrical currents flowing through the atmosphere, which were detected on the ground by the magnetic field sensing instruments. But then a couple of days later, or a day or so later, all the data basically went off the scale. You can see in these charts, you can see the pens going off the scale. Basically, that's an enormous geomagnetic storm kicking off as this huge amount of solar material arrived at the Earth and triggered a massive geomagnetic storm. And we know at the time also from contemporary accounts, here is just one of them, there is the record of a conversation between two operators on the Boston to Portland telegraph line. So remember, this is the Victorian internet, and you can see one operator asking his colleague at the other end of the line to disconnect their equipment for 15 minutes because their signals are being interrupted by auroral activity. And what's actually happening is the aurora overhead are symptoms of huge electrical currents flowing through the upper atmosphere, and those are actually inducing magnetic disturbances which themselves set up electrical currents in the telegraph lines, and it's interfering with the power in the telegraph lines. And these two operators are able to talk. So when one asks the other to disconnect, he confirms it's disconnected, and then the Boston operator says mine's disconnected and we're working with the auroral current. So they've not plugged in their sets, they're able to talk to each other by the current flowing through the lines being generated by space weather. And actually, in that case, they seem to be able to carry on and they go on sending messages to each other. But there were other examples of telegraph stations burning down and telegraph operators receiving electric shocks. And there were lots of press reports at the time of the aurora being visible in the Rocky Mountains or from San Francisco several nights running. So at very southerly latitudes where you wouldn't normally expect to see the northern lights. So this is perhaps a good starting place to think about, well, that was a really big event. You know, what would happen if that happened today? What is a kind of a reasonable worst case scenario for the UK? And so actually at the time, if you lived in the northwest of the UK, so I'm at Lancaster University on the west coast of the northern part of England, and this would have been the locomotives that sped past or sped that through Lancaster at the time. So at the time of the Carrington event, technology was steam and iron, coal. It would have been pretty bomb-proof to the effects of space weather. There was nothing here that was going to be disrupted by electrical currents flowing through the ground and flowing through grounded infrastructure. However, if you fast forward 150 years, the technology we rely upon today looks a little bit different. And so this kind of technology is actually much more susceptible to electrical currents. So for a start, our trains are reliant a lot on electricity. So we rely upon the power grid being able to supply electricity. So disruption to the power grid could potentially disrupt train travel, for example. Actually, trains rely upon GPS systems to know where they are. They rely upon lots of communications and signaling, which some of those subsystems are impacted by space weather effects. And so one of them I've got here would be track circuits. So if you're a rail enthusiast, you may know this, but if you're not, then you might be surprised to learn that one of the ways you know if a train is in a particular section of rail is that you basically create an open electrical circuit which is connected to the signals. And when a train comes onto that section of track, you can see here a picture of the train axle short-circuiting across between the open circuit which you set up between the rails. It actually causes the signals behind the train to show red. And so the idea is you can't have a train run into the back of another train because the system knows there is a train in that section of track. Well, if you start thinking about inducing electrical currents into the rails, because they are long pieces of conductive metal and electrical currents will geomagnetically induced currents due to space weather could flow through them, then you can see that these systems can be interfered with. And there are some examples of track systems like this being disrupted by space weather and the signals not showing the correct signal. So even everyday mundane things like trains can be impacted by space weather. Now, the trick is, of course, is to think, well, how do we deal with that? And this is where I wanted to touch on some of the sort of society and policy issues a little bit more, is just that if you are a train operator, I did a bit of work with the government department recently, looking and talking to the rail sector about how you deal with these things. And train operators, you know, if this is a risk which is probably unlikely to occur in the next week or two, train operators, you might argue, have more important things to worry about. They have leaves on the line, which could cause problems. They have bad weather. They have normal breakdowns. They probably have to think about security and terrorism. They probably at the moment have to think about social distancing and measures. So making the space weather threat come high up on their things to worry about in any given day or month or year is quite challenging, which is completely understandable. That's the wicked dilemma about these high impact, low frequency events. However, what you can do is start to think about, well, could we use any of our other, what you'd call business continuity planning to adapt for space weather? And so I've just got a couple of grabs from the sort of the media here of what happened the year before last, I think it was, when a train had to be, came to a halt due to snow outside of a station in London. And the rule of thumb is that if a train comes to a halt, in this case brought to a halt by snow, you know, the passengers will start to get off the train after about an hour and a half, regardless of what you tell them. And of course, they are then potentially wandering around on a track where there may be other trains still moving. They may be wandering around on tracks which are conducting geomagnetically induced currents, which could potentially be a risk as well. It's not a very well understood risk at all. Generally, you don't want people wandering around on the railways. So in this particular case, you can see here from photos taken by people's smartphones, the train is being evacuated and the emergency services are there to help get the people off the line. So if a train was stranded, for example, due to signalling or a power issue due to space weather event, you might think we could just evacuate the train. However, if a large space weather event also knocked out a metropolitan area, it may be that the emergency services would have an awful lot to do, and evacuating people from a train may be not their top priority. And so something you could think about is in adapting the normal business continuity plan for a train, for example, into the space weather scenario, is how much of your normal planning relies upon the emergency services being present, and they may not be present, or relies upon radio communications, which may also be impacted by space weather. So it's about that coming together of several different risk factors at the same time and trying to plan for those accordingly. And certainly, if we think about more generally, geomagnetically induced currents causing damage to the power grid, it just so happens that coincidentally, Lancaster does research on space weather, but also we do quite a bit of environmental research here at Lancaster. And some of my colleagues in the Lancaster Environment Centre wrote a report called Living Without Electricity, which was based on the experience at Lancaster of Storm Desmond in 2015. So in the UK, we name our winter storms, and to most people, they will have forgotten about Storm Desmond. But actually, in that first weekend of December 2015, Storm Desmond caused a flooding of the city's main substation. So the water was 2 meters deep in the substation. As you can imagine, the power went off. And so actually the entirety of Lancaster, so 60-something thousand properties, about 150,000 people, were left without electricity, most of them for about 5 days. So in some ways, even though it was caused by a regular weather event rather than a space weather event, it gave a really interesting insight into what a city could do when the power goes off. And of course, the first thing that goes is all the lights, but then after a couple of hours, all the mobile phone masts shut down because their uninterruptible power supplies, their batteries are flat. It's at that point you realize that your cordless phone that is a landline at home still relies upon mains electricity, and unless you've got a physical corded phone to plug in, you can no longer phone anybody. And all sorts of interesting things start to happen. So even though the trains were running through Lancaster throughout this particular episode, because the overhead lines were powered by regions outside the affected area, the trains didn't stop at Lancaster because there was no lighting at the railway station. And so it being winter, you couldn't have people wandering around a dark platform and falling onto the line. So they had to shut the train station. So there are lots of knock-on effects of, say, power interruption, which could be driven by space weather or other such things, which we don't really think about very much. Now the solution in the end for Lancaster was to bring in an awful lot of diesel generators. And so you can see a picture of one here. These lorries with diesel generators on were dotted around the city. And for several days, Lancaster, the entirety of Lancaster, 60,000 properties, was running on diesel generators. However, you could not do that had it struck Manchester or the southeast of the UK. And so how we deal with these things, we can learn an awful lot from how we deal from non-space weather events and apply that to space weather. And so to finish off then, what I'm going to do is I'm just going to try and highlight some of the things that we're doing at Lancaster. And this is actually going to highlight a recent publication by Neil Rogers, who's led some work here at Lancaster as part of the SWIGS project, which is the Natural Environment Research Council's highlight topic project on space weather impacts on ground-based systems. And so what Neil's been working on in this case is trying to create a global climatological model of extreme geomagnetic field fluctuations. So really, how bad can those fluctuations in the magnetic field at ground level be? Because we know that it's those large, rapid fluctuations in the magnetic field that drive currents, for example, in power grids and other ground infrastructure. And there is a link to the paper and the DOI. This was published in January, so if you'd like to know all the gory details, I'd encourage you to go and look at that. But basically, what Neil did in this study was he took data from the SuperMag network or project, which brings in data from ground magnetic observatories all over the world. And here's a map of all the stations he took data from that had data for more than 20 years. And the color coding of all these ground-based stations is showing you what the 99.97th centile is of the variation at each site. So it's showing you how strong the most extreme measurements of magnetic field are at each site. And so they're color coded according to what you see on the right hand side. And what you see isn't surprising to space physicists, is that the sort of the greens and the yellows and the oranges getting towards the reds occur generally in this region around the sort of auroral and subauroral zone, this crown around the magnetic pole where we see the northern lights. So these are the data set that Neil's analysed here, but what he's done is he's used some extreme value theory to look at the kind of distribution of those extreme values. So you take your many decades of data, throw away the overwhelming majority and just keep the most disturbed measurements, and you look at that distribution. So you're looking at the tail of a distribution of values, and you try and fit a distribution and get a shape so you can understand that, because once you have the shape, you can extrapolate forward and think about what are the most extreme values you're going to get over a given time scale. And without going into all of the analysis, I'll just shortcut to some of the results. What you can see here is on the left-hand side is a plot showing the 200-year return level of magnetic disturbances based on data that has been looked at of several decades worth of magnetic field measurements. And so what this is saying is how, if you look at the kind of event that occurs once every 200 years, how many nanoteslas per minute is the field varying? In other words, how fast is the field varying? And this is presented as a function of geomagnetic latitude. So actually it's absolute magnetic latitude. So imagine everything's in one hemisphere, from the equator on the left-hand side to the pole on the right. And unsurprisingly, what you see is that as you get towards mid and high latitudes, the return level goes up. So what this is saying is that somewhere at sort of 50 to 60 degrees magnetic latitude, the return level is about 2000 nanoteslas per minute, but we've got some uncertainties on here that give you the confidence intervals, the 95% confidence intervals. And so it could be up to 10,000 nanoteslas per minute at sort of 50 to 60 degrees magnetic latitude. So that's saying once every 200 years, you will get an event which is perhaps thousands, maybe even 10,000 nanoteslas per minute. And that's, for those of you who are interested, will know it is quite a rapid fluctuation. And so that would be something we'd need to have a think about in terms of how our technology would interact with that. And so there are other folks in the UK who are modeling how the grids would respond. So we can use these kind of data, these models, to input scenarios into those grid models. And on the right-hand side is actually just another side effect of this analysis, or another way of presenting it is you can take a best fit through this distribution, and you can look at it at different return levels. And so the blue one at the bottom is showing what the 5-year return level would be. And unsurprisingly, it's not very big. It's a few hundred, maybe just under 1,000 nanoteslas per minute. When you go up to 500 years, you might be up to 10, 20,000 nanoteslas per minute, occurring once every 500 years. But what's interesting is the shape of the distribution changes. So as we go for increasingly rare events, they actually come down to lower latitudes. Now, again, that's not very surprising when you think about the way that the natural system works, because when the system is very disturbed, the aurora moves to lower latitudes. So these very big events will have a bigger impact at lower latitudes. What's also quite interesting here is that if you think 50 to 60 degrees is where we see some of the very interesting stuff going on. Lancaster at the moment, which is about halfway up the British Isles, is about 56 degrees. So depending exactly where you are relative to this peak can have a big impact in the kind of distributions of these quite rare events you see is. And we know that the pole is moving. So for example, if I go on to the next slide, we know this is just a plot from the internet, but we know that the magnetic pole is shifting. So our susceptibility at any position on the surface of the Earth to how frequently we see these events will shift over time. So really, it's not just space weather; it's space climate as well. It's how is space weather changing over longer time periods is going to become quite important to us. And then the other thing that Neil was able to do in the study he led was actually break the data down into and looking at it in a variety of different ways. So in the center of this slide, we actually have a plot showing magnetic local time from 0 to 24. So we go from midnight through noon back to midnight again at all positions with an absolute geomagnetic latitude going from from the equator at the bottom up to the pole on the top. And what the color coding is showing really is the likelihood of where you're likely to see the most extreme values. And what it tells you is that you get a big hotspot in the pre-midnight sector in the auroral zone, which is basically the geomagnetic substorms, the elements within geomagnetic storms that create large fluctuations of the magnetic field at ground level. We also see in the cusp region, so at noon, at the very high latitudes, we see how the interaction with the space environment generates magnetic field fluctuations at ground level. But we also see some other interesting features going in here. We can see there's a band of features here, which are probably what as space physicists call PC5s. So these are pulsations in the magnetic field, and they're going from lower to higher latitudes as we get closer towards noon. And we can see some sudden storm commencements at low latitudes in the noon sector as well in this. And there's a sort of V-shaped distribution of these events as well, which we're not entirely sure we fully understand. And so one thing you can take that data is you can visualize it and put it into a fitted spherical harmonic expansion. So that's for this study, you can actually recreate the data if you like, if you need that for a model. So that's something that's published alongside the paper with this analysis in. But also you can cut this data in lots of different ways. And so on the right-hand side is if you take the data and bin it by the direction of the interplanetary magnetic field in space, then unsurprisingly, you find out that under northwards IMF, so northwards pointing interplanetary magnetic field, the cusp is really where the hotspot of activity. And the southwards IMF, it's actually tends to be the substorms at the pre-midnight sector in the auroral zone, and that the lower latitude sun commencements are typically unaffected very much by the direction of the IMF. And so we can cut this data lots of different ways, and I'd advise you go and have a look at the paper. You can see how it breaks down by latitude, local time, IMF, and a variety of other things. So we're getting a handle on what these very extremes are like. How is that useful? Well, many members on this call at the moment or listening to this seminar at the moment are members of the UK Space Environment Impacts Experts Group, which is an independent group of space weather experts that provides advice to UK government bodies. And that was set up a decade ago now with involvement from the Civil Contingencies Secretariat, which is part of the Cabinet Office in the UK government. But basically, what this tells you is that there are folks up and down the UK community working hard with the people who make the regulations, who draw up the risk registers, to try and get this information out into those people who need to use it for the planning. And then, so really, I was just going to trail that there is a paper which is in its final stages of preparation for submission to the Journal of Space Weather and Space Climate, which is going to be the development of space weather reasonable worst case scenarios for the UK National Risk Register. And that will include, that actually refers not only to the paper I've just been talking about by Neil Rogers, but across the suites of different areas of space weather. So you probably want to keep your eye out for that when it comes out in the not too distant future, we hope, if the reviewers are kind. And so it's at that point, I think I've been talking probably too long, so I'm going to stop talking, but I'd be very happy to take any questions if anyone's got any. Thanks very much.
Thank you, Jim. That was really interesting. And that paper looks really interesting too. So I'll look forward to that. Look forward to reading that. Yeah, so now we reach the question time. So if you do have a question, just use the hands up signal or pop it in the chat. So we'll just give everyone a minute or two to think of their questions. But yeah, that was really interesting. Any questions, people? Whilst they're thinking of their questions or typing it up, I had one about the way that we can mitigate these space weather risks? So, for example, when you were talking about the train lines, are there ways that they can make the existing technology more resistant to these hazards? Is that one way, or do you recommend that they just make plans for when the situations occur?
Yeah, that's a really good question. I think you probably could. There is some engineering you can do. I think we're probably away from that because these systems are already there and haven't been engineered in that way. Ultimately, so things like the power relies upon the power grid. Okay, so it's not just a 3-pin socket plugged into the normal power grid. That, you know, train lines generally have their own electricity systems, but ultimately they draw power from the grid somewhere. So I mean, things like that, making the grid more resilient would help. And in that, so as people like National Grid in the UK have done a lot of work to try and understand these risks and figure out what you do. And so, for example, the obvious thing to do might seem to be that you just turn off all of the power grid and everything will be fine. I mean, apart from the fact that that's quite a difficult decision to make, you know, dear Prime Minister, could you please turn off, you know, we need permission to turn everything off. It's probably more likely that you turn the whole grid on. So you would cancel maintenance or any lines. If you knew something serious was on the way, then it would probably be more sensible to cancel maintenance that would take large sections of the grid out, make sure you've got as many lines open as possible, and then geomagnetic induced currents can flow through grids, for example, in a variety of different ways, and you're not channeling them through just 1 or 2 bits of the grid. So there are sometimes quite counterintuitive things you can do that could well help. And I guess really we're in that stage of trying to now understand those better.
Yeah, that's really interesting. I'll stop live streaming and, oh, we do have a question. So Martin Archer asks, what is the advice on what to do when your emergency procedures are heavily reliant on radio or emergency services?
Yeah, that's the really good one. And I'll dodge that one. It's probably not for scientists to tell organizations how to manage without those things, but you would probably want the scientists to be saying you shouldn't necessarily assume that they are there. But what it probably means is you're going to have training and procedures that would build into, you know, and when you do your risk scenarios and you do your exercises, to not always assume that things are there. I mean, it's a given. My understanding from safety engineering is it's a given that usually it's not through a system failing that you get a bad accident or something terrible happening. It's usually when several things fail all at once and they come together, in that, whether it's a plane crash or whatever. And so I think the advice would have to be to take your existing models, utilize them where possible, but then also re-examine how your disaster or what your business continuity plan might be challenged by multiple failures that you wouldn't normally expect to have.
Okay, great, thank you. Next question from Steve Milan is, how resilient does the national grid feel it is to space weather effects given NEO's statistics?
So I know that the National Grid have been working quite closely with, for example, the British Geological Survey who have a grid model which suggests roughly how severe some of the induced currents could be in the lines. And so I think my latest understanding is that the National Grid would feel that whilst they wouldn't be completely without impact, actually it would be relatively small for most of the kind of scenarios we're talking about here. Now, of course, as with all these things, the proof is somewhat in the pudding, but certainly that then factors in that you would do some of the mitigations I was suggesting. So you would take things out of, you know, if you had a line shut down for maintenance, you would try and bring it back in to give yourself more resilience. So the proof of the pudding will be ultimately when, and it probably is when, not if, the space weather scenario comes up that we get a severe space weather. I think the UK National Grid is actually quite far ahead of a lot of other countries in thinking about this, and they've been talking to the scientists throughout. So I think we're in a reasonably good place. I think what's worth also thinking though is that there are examples, for example, in South Africa and other countries where there have been demonstrated to be problems with geomagnetically induced currents in perhaps environments or locations you wouldn't necessarily think about it. So I think there's some more work to be done on raising that awareness there.
It's really interesting. Next question. So they ask, Jim has highlighted UK risk mitigation. Is there collaboration on mitigation across, for example, the EU?
Yes, I believe there is the short answer. Yes. So and also our grid isn't entirely disconnected from Europe. So we have interconnects, for example, on the power grid issue. So yes, and no, I'm not so much an expert in satellites, for example, or radio communications, but there are a number of cross-cutting European-wide projects to look at these risks. So I think the short answer is yes.
Okay, we've got quite a few questions coming up now, so I'll just try and go through more. Next from Colin Forsyth, in the spherical harmonic fit data, why does the substorm effect on the night side appear to be larger during BZ between 2 or -2, rather than BZ is less than -2? That question is in the chat in case you want to read it.
Yeah, no, that's well spotted, Colin. I think you're referring to this. So this slide. So the data on the right hand side is data. It's not spherical harmonic. So I think the short answer there is the color coding here. I haven't gone into all the details. The color coding is normalized to the cells. So those red colors aren't quite comparable between each slide. So yeah, I'd refer you to the paper to look at some of the details of that.
Okay, great. I put the link into the nugget, and I'll have the link to the paper as well. So if you want some lunchtime reading, check it out, everyone. Next question, this might be our last one. Are there significant improvements in predicting if a solar event is going to hit Earth's magnetosphere so we can avoid false alerts?
Oh my word. So there are probably many people in the audience of this particular seminar who are much better qualified to answer that question. So I would suggest that the answer is that capability is improving all the time. I know there's things like the L5 mission that are proposed, which would look on the Earth Sun shooting gallery side on to try and make better predictions of those. And I guess the holy grail one day will be, can we measure the direction of the interplanetary magnetic field wrapped up inside large coronal mass ejections heading towards the Earth? And that's what we're going to be aiming for. So I think we're getting there, but I think we're probably, it's not going to be in the next 6 months that we're going to suddenly improve that. So I think, we need to keep looking. But yes, I think I would be very interested to see an updated seminar from some of the people in the audience on this, on that sort of prediction side of things.
Yeah, if anyone wants to volunteer to give that seminar, send us an email. Okay, I think we can squeeze in the final question. How much do the orientation and length of power lines and the resistivity of the surrounding rock affect the damage due to GICs?
That's a really good question, and it makes a huge difference. So the conductivity of the Earth's surface you're on is very important. And so my colleagues at the British Geological Survey, I know, give a tremendous amount of thought to that. And so different parts of the UK are more or less susceptible to them. Apart from their geomagnetic latitude, you might expect northerly latitudes are more impacted by space weather than southerly latitudes because you're close to the magnetic pole and the northern lights and all that stuff. But also the geology of the UK changes as well as we go, as does your proximity to coastline, because there is an effect of the conductive oceans as well. But also the orientation length of the power lines is very important, because as east-west currents, most of these electrical currents flow in the east-west direction will tend to create north-south disturbances in the magnetic field. And so east-west power lines are disturbed differently than north-south power lines. And actually, as part of that study I was showing from Neil Rogers, we start to look at the directionality of the dB by dt, the rate of change of the field. So does it matter how much, it's not only does the strength become important, but also the directionality of the change in the field. Both of those are going to be issues we need to understand better than we currently do. So that's a really good question.
That's really interesting. Okay, so I think that brings the question time to a close. So thank you everyone for coming and attending the seminar, and thank you, Jim, for giving a really interesting overview of space weather. We'll be circulating details for the next seminar taking place next month via the mailing list, and you can also check out our website for details on past seminars, links to watch those, as well as seeing what's coming up next. So thank you everyone, enjoy the rest of your day, and goodbye.